Hi, my name is Savannah Westies, and my team members are Chad Clausen, Peyton Cook, Josh Stamba, and Laura Diop. And we will be presenting section 12.6, kinematics and projectile motion. Projectile motion is the study of a free flight of an object. So like kicking a soccer ball and seeing where it lands and how high it goes, or throwing something out of a window. The rectangular coordinates are usually used, so x and y components are what we look at. Only acceleration is due to gravity because you only look at, there's no air resistance, so you only look at how it drops.
I am Peyton Cook, and I am going to explain projectile motion and how it's broken into its x and y components. I'm going to start off with the x components, which is in the horizontal direction. And the equation we use for position of a particle is given as x equals x naught plus vxt. So x is just the position of the particle at any point in time. X naught is the initial starting location of the particle on the x-axis. And Vx is the, V naught x is the initial x velocity. And then t is, of course, time, which is measured in seconds, typically. And notice in the horizontal direction that velocity is constant. That is because there's no acceleration, such as gravity or wind resistance. We're assuming that the particle is just going to move at the same velocity in the x direction. Vertical motion is slightly different than horizontal motion because we have gravity. Gravity changes the equation that we use for the position of the particle. So I'm going to write out the y equation for position. Y equals y naught plus v naught y times t plus 1/2 a t squared. And so y is still the y position of the particle at any point in time. Y naught is still the initial starting point of the particle. We still have t, but now we also have a. And a is the acceleration due to gravity. We're going to use the value that a equals negative 9.81 meters per second squared. So including that in our position equation in the y direction means that we now have a changing velocity in the y direction, unlike horizontal motion where there is no change in velocity. So if you take the derivative of this equation, you get the equation for velocity of the particle in the y direction. And that becomes Vy equals v naught y plus at. It's just doing the derivative of the y position equation to get the y velocity equation. We can also rearrange these equations into another equation which does not have time in it, and that is Vy squared equals v naught y squared plus 2 ag times y minus y naught. And ag is just the acceleration due to gravity. So that's a summary of how you break down projectile motion into its x and y components. This makes calculations quite simple, especially in the x direction where there's no acceleration, but even the y direction, it's not too hard to add acceleration due to gravity in there.
All right, so my name is Chad Clausen, and I'm going to be talking about what we're actually doing for this experiment. The main idea of the experiment is that we're going to be hitting two armies that are right here and here with a ball that is shot from a cannon. And the main idea is we have to get it through a certain hoop right here that is kind of representing a hole in the wall. So first of all, we're going to shoot the cannon off of a certain height right here. That'll be 1 meter off the ground. And then we're going to move it up 1 meter and shoot it off of the ground. And both of these will go through the hoop and then hit the different armies. Okay, so the initial conditions that we have for this experiment is the initial velocity is 4.66 meters per second that the ball is going to be coming out of the cannon. And we determined that from a previous experiment. And we also are going to have the cannon be at a 45-degree angle.
Hi, my name is Laura Diot, and I'm going to explain our equations that we use to find where to place the hoop and where the landing position for our second projectile is. So first what we need to find is the x and y position for the hoop and the landing position. So we'll put that under find. X position for the hoop, the y position for the hoop, and x2. In order to find those, we need a lot of givens. So we know that acceleration equals 9.8 meters per second squared due to gravity. We know that the landing position for projectile 1 is 3.47 meters. And then we know the starting positions for both of the cannons. All right, the first thing we're going to do is solve for the x and y positions of the hoop. So as you can see, I use the kinematic equations and set them up for the y of the hoop from the first position, the y of the hoop for the second position, and the x positions for the hoop. Now all of these, the x's are going to be equal because we want both of the projectiles to go through the same point. So these two will be equal, and these two will be equal. Using our givens, we know that the y position, starting position for hoop 1, is 0.268 meters. The starting velocity is 4.66, and then we want it just in the y component, so we do the sine of 45. Over here we have the acceleration times 1/2 times the time. We do the same thing for the second y position. This one starts at 1 meter high, and the rest of the equation is pretty similar. This one starts at 1 meter in the x direction, and this one starts at 0. So once we solve all these out, knowing that these two are equal and these two are equal, we get the x position of the hoop equals 2.42 meters, and the y position of the hoop, which equals 0.778 meters. The next thing we want to solve for is the landing position for projectile 2. In order to solve this, we're going to use the same kinematic equations we used to solve for the hoop position, but the y position is going to start at 0 because we want where it hits the ground. We have the starting position of 1 meter high, 4.66 meters per second is the initial velocity, and then we have gravity is 9.8 meters per second. We use this first one to solve for time so that we can plug it into the second equation in order to solve for the x distance. And once we work these out, we get x equals 2.96 meters.
Hello, my name is Joshua Stombaugh, and I will be showing y'all the setup we have for our demonstration. Now, after calculating all the positions we need for our demo, we have brought in a projectile launcher thanks to Dr. Ball. And right now we have it set up at 1 meter high. That's where it's going to be first shooting off. And then our second position will be 1 meter in front of this, on the ground at 1 meter, 1 meter in front of that. Here we have the tail end of our experiment where the ballistic ball will come and hit. We have a balloon located here at 2.96 meters away, and a balloon located at 3.47 meters away. And both of the balls will be going through the hole here in the cardboard where it's located at 0.78 meters off the ground, and this is where the projectile arch will cross, and the ball will come and hit both of these and will pop them, and the army men will fly away and we'll win.
Ready, aim, fire! Ready, aim, fire!
Yay! Yay! So as you can see from our experiment, dynamics lets you do a lot of things, like pop some balloons or many other things, like see how far you can kick a soccer ball based on how hard you kick it.